All right. So as I was saying in the last video, this discovery in around 1832 by Michael Faraday, an English physicist, was a big turning point for humanity, and it's in fact it's so common today that we almost don't even think about this idea of electromagnetic induction. But when you look around in businesses and homes, and you look at the wall outlets, when your cell phone dies and you have to plug your cell phone in, or you have to plug your computer in, or whatever, the lights come on and things like that. We don't even think about that. So what electromagnetic induction is how electricity is created. Um, um, for the most part. Okay. Of course, before electromagnetic induction, we could create electricity using batteries, but batteries tend to be very, very expensive, way more expensive than this method of creating electricity. And so let's get into it. What did Faraday discover? As I said, can magnetism create electricity? And so what Faraday did is he created some loops of wire, and of course he had to build. Even this is why it took so long from 1820 to 1832. He had to build all this stuff from scratch, and he didn't really know how it was going to work. He performed lots and lots of experiments. He he made some great discoveries besides electromagnetic induction. Anyhow, so this is basically what it is if the magnet moves through the coil, either up or down through the coil, then the meter would deflect back and forth. And that is basically magnetism through motion creates electricity. And that's electromagnetic induction. That was his great discovery, and that really changes the human race forever. I mean, all right. So what is a generator? So this is the typical. In the last slide, I showed you that you're moving the magnet in and out of the in and out of the coil, but really, magnets tend to be very heavy, and so what happens in an actual generator is the coil of wire is spun in a permanent magnet. So the magnetic field is passing through this coil, and this coil starts to spin. And that creates electricity, and that's how we create. And of course, what we create is what's called alternating current, or AC, right? A sinusoidal wave that just keeps going and going and going. Generally, what we do in electric circuits is when we want DC, is there's circuits that can change AC into DC. Okay. And that's done locally in the power supply of most modern electronics. All right, so the question, what I want you to think about for just a moment is, how do we spin this coil of wire? And if you think about when this was done, when Faraday made this discovery, the engine that was the best technology on the planet at the time was, of course, the steam engine. And really, believe it or not, we still use steam today. The wire itself is connected to, mechanically connected to a turbine. What's called a turbine is just a giant cylinder basically with fins on it, and I'm not really showing that here, but steam, really high pressure, high temperature steam passes over the fins, and that causes the turbine to spin really fast, and then mechanically that spinning motion is coupled to these coils, and really that's how electricity is generated, whether it's a nuclear power plant or coal burning power plant or an oil burning power plant or even a gas burning power plant. It's really all about boiling water. So in a nuclear power plant, the natural nuclear reaction boils water. The water passes over the turbines, or you can have a coal burning power plant. The steam passes over the turbines and gets this thing spinning. All right, so that's just a little bit about the way electricity is generated, and this is not important. All right, so now we come almost immediately to this idea of what are called transformers. And so the problem with sending electricity, so it says high currents, you get really large resistances in the wire. Okay, so if I sent a lot of current from Rock Hill to, I don't know, to Columbia or something like that, we would have enormous losses. And you're creating all this electricity, you're burning coal or whatever, however you're doing it, and you're really just wasting the electricity. It's just going into heating up the wire, which we'd rather keep it as electricity. So what humans discovered is this idea of transformers. What a transformer does is it changes, it keeps the same amount of electrical power, but it changes current, large amounts of current, into large amounts of voltage. And vice versa. So you create these using the transformer, you create a large amount of voltage. You send that across the wires, and then when that voltage gets to nearby, where it's a business or a home, then there's another transformer that does the reverse process, changes this really high voltage, steps it back down into ordinary voltages that you use and that come into your house, like 240 volts, and then your house basically changes that into 120 volts that you plug into in your outlets. Okay, so the basic idea is the power in equals the power out, and let's see. So there'll be a certain number of turns of wire on one side. The one side, usually the left side, we call the primary, and then there's a certain number of turns on the other side, turns of wire. We're going to call those N sub P for the primary, N sub S for the secondary, and depending on the numbers of turns of wire, we're going to either step up the voltage or we're going to step down the voltage. Okay, so this, for example, would step down the voltage because there's less turns on this side than this side. I'll get into that a little bit later, but this one, for example, would step up the voltage. The voltage in the secondary is going to be higher. All right, we'll do examples of all of those. So this is our first transformer equation. It says the voltage in the primary, so that's this side, divided by the number of turns in the primary equals the voltage in the secondary divided by the number of turns in the secondary. And so this is used all the time in transformers. We're going to do lots of examples with this. And the other equation is really this: the power in equals the power out. What that means, of course, is the current in the primary. Here, let's go back. The current in the primary, whatever current is flowing through these wires, times the voltage that is across these wires, equals the current in the secondary times the voltage in the secondary. And that's where we get the second equation that we're going to use. All right, let's do a quick example. So again, the left side is this is the primary. There's a certain number of turns in the primary, so those turns, which I have as coils, we're going to call N sub P, and the turns in the secondary are going to be called N sub S. So the S is going to stand for the secondary, which is whatever's on the right, and P stands for the primary, whatever's on the left. So there's some voltage on the primary, and the voltage is between this point and this point. And the same thing with the secondary, right? So there's going to be a voltage in the secondary, and the voltage is from here to here. If you put a meter there, you would see some voltage. And then there's a current. We're going to say I primary. And so that current is running through these wires, these loops of wires, and through electromagnetic induction, as the current goes through these wires, it's going to cause a magnetic field. That magnetic field will be felt by the secondary turns, and it will create a current in the secondary, right? And so we're going to call that I secondary, and so that secondary current will go along those wires. All right, and this is it. So here's the equation. So just as a reminder, the voltage in the primary divided by the number of turns in the primary equals the voltage in the secondary divided by the number of turns in the secondary. All right, and so that's this picture right here is what we have, and the fact that the power in the primary equals the power in the secondary, that's always true. And so what this equation implies is that, what is power? It's current times voltage. So the current in the primary times the voltage in the primary equals the current in the secondary times the voltage in the secondary. And this is really this equation right here, I'll call that number 1, and this equation right here, I'll call this number 2, which is this really. I mean, it's the same equation, number 2, as is this, right? That they're identical, but we really use it more in this form. Okay, so let's see. Let me do a quick example. So let's say that I had some number of turns in the primary. Let's say, and the number of turns it's just a number, right? It doesn't have any units. Let's say I had 100 turns, okay, in the primary, and I had in the secondary, the number of turns in the secondary was I don't know. Let's make it 1,000. Okay, 1,000 turns in the secondary. If I had a voltage in the primary of 50 volts, let's say 50 volts, we could ask the following question: what's the voltage in the secondary? And also, we could also ask the following. We could also ask, if we knew the current in the primary, I primary, let's say the current in the primary was, I don't know, how about 2 amps? What's the voltage? What's the current in the secondary? So what's the current in the secondary? All right, so we'll answer those 2 questions. And we could also ask whether it's a step-up or step-down transformer, and what the power in the secondary is. All right, so is it step-up or step-down? Or let's start. We'll just go with what's the power in the secondary. And so we'll answer all those questions. All right, so the first one, of course, we can answer is what's the power in the secondary? The power in the secondary equals the power in the primary. And what would be the power in the primary? Since I know both the voltage and the current in the primary, I can work that out right now. The power in the primary equals 50 times 2, right? So 2 amps times 50 volts, but that is also the power in the secondary, right? Which of course amps times volts gives us watts, and so that's going to be 100 watts. So either that's the power in the secondary, that's the power in the primary. I'm going to pick this up on the next video.